Hello. For Chapter 5, as a recap, just recall that something that you've been learning about are definite integrals, in which you have some sort of function. You can just call this f of x. And since you're defining this integral, you're restricting its limit from a lower bound. We can call it to be 0 or a. And you're giving it some closure, like a gate. So we can consider this to be b. So the specific definition of integration is that you have a lower bound to be a up to b of some random function, but usually the functions are given to you, f of x dx, and then you're just applying the rules of integration to find out how much area is under the curve. So I'm going to be taking poems from the book 12, 13, 14, and if we have time, 16. Just keep in mind, with rules of integration, there are some definitions that you have to, I wouldn't say memorize, but you just have to be sure to apply them carefully. Meaning that if you have some random base, like 5 to the x, to integrate this, then you just copy and paste the 5 to the x, but also include the natural log of 5. So if you have a random value again, 10 to the x, it's just a copy and paste 10 to the x over the natural log of 10. So no matter how complicated the numbers are, you can say 8/3 to the x power. When you integrate this, it will become the copy and paste version, so 8 over 3x over the natural log of 8/3. And so forth. So 1.05 to the x, which is equal to 1.05 copy and paste over natural log of 1.05. Cool. So let's get on to it. So number 12, to find integration from 1 to 2 of 2x dx. And if you see that there's a base and it's raised to an x power, then we have to apply the rules of integration, that this will become 2 to the x, copy and paste over the natural log of 2. And when you do that, you're finished with using the integration symbol, and now you have to apply the bounds. This is from 1 to 2. When you're applying the bounds, you have to copy and paste the 2 wherever you see x. Subtracted by, copy and paste this, the inside part, the yellow, and replace x as the lower bound. So I'll show you what that looks like. 2 over natural log of 2. And this is subtracted by 2 over the natural log of 2. And I'm just going to be copy and pasting the bounds from here. So applying 2. And this is applying 1, the lower bound. Now carefully work out the calculations. 2 to the second is 4. And 2 to the first power is 2. Copy and paste everything else. So natural log of 2 subtracted by 2 natural log of 2. And hey, what do you know? The denominators are the same, so you can just subtract the top. So 4 take away 2 is just 2 natural log of 2. This is considered definite, meaning that there will be no cases where you have to do plus c. I know many instructors like to take many points away when you forget to apply plus c, but just recall, anytime when you don't see any number here and here, you always have to do plus c once you do the integration. I'm sure questions like that will come up in the near future, so I'm going to help you more with that. So what this means visually, if you do 2 to the first power, it's here. So when you are at 1, you are at 2. And once you are at 2, 2 to the second is 4. So here's 4. So it's going to look like this, and you're trying to find this funky area. This funky area is actually 2 over natural log of 2. So when you divide this out, this is like 2 divided by natural log of 2. And if you type it into the calculator, natural log of 2 happens to be 0.693. And when you do 2 divided by 2,693, 0.693. Then you will get the decimal version of the answer, 2.89 square units. So the area under the curve of this function will be 2.89 square units, or many instructors like to use exact numbers. So 2 over natural log of 2 is perfectly fine as well. Cool. Onwards. Question number 13. The integration from 1 to 4 of x squared plus x. The fact that we're working with the sum of the polynomial terms, I can just separate the parentheses out. So this becomes x to the second plus x dx. And this is from 1 to 4. And this is pretty direct. We can start integrating. So j plus 1, j plus 1. Because I'm taking the 2 by adding one more degree to it. As for the x, this is plus. This one already has a 1, so I'm going to do 1 plus 1 over 1 plus 1. And we're applying the bounds from 1 to 4. I'm going to simplify a little bit further out. So 2 plus 1 is 3. This is 3 plus x to the second to the second. And then from here, we can be able to apply the bounds. This is from 1 to 4. So I'm going to replace 4 in for x, subtracted by, and it applied 1 wherever x is. So this becomes, I'll include a 4 first, and then 1 second. And then again, it's just a copy and paste. So this is over 3 j2 second. And what's in middle is the subtracted symbol. And this is 4, 3. And carefully work out the math. So 4 to the third is 64. 4 to the second is 16. Minus 1 to the third is 1 divided by 3, and this is plus 2. We see 3, 2, 3, 2. So I'm going to multiply so we can see their LCDs come together so we can add just the top. So this is times by 2, this is times 3, times 2, times 3. Carefully work out the math. 64 times 2 is 128 over 6 plus 48 over 6. Subtracted by, this is 2, 6 plus 3, 6. And again, careful calculations. This is 176 subtracted by 5, 6, which in the end will become 171 over 6. And it seems like 3 is a common factor for that, so divide by 3. Divide by 3. And this one becomes 57 over 2. So what this means is that if you were to graph this out, we're going from 1 to 4. 1, 2, 3, 4. Now this funky looking function, f of x. And the area underneath the curve will be 57 over 2 square units. Or you could just divide this out so that you get 28.5 square units. So either of these two works perfectly well. This one, question number 14. Before we do any integration, I'm going to use FOILing to expand this out. 3x plus 1, 3x plus 1. And be careful with your FOILing from here. So 3x and 3x gives you 9x squared, 3x times 1, 3x. 1 times 3x, so this is another 3x, and 1 times 1 plus 1. Add your like terms, and then you get 9x squared plus 6x plus 1. And again, we're integrating this from 1 to 5. And now we can apply the rules of integration. 9x, we're going to increase this by 1 more degree, so this becomes 2 plus 1 over 2 plus 1. This one already has a 1 to it, so I need to increase that by 1. 1 plus 1, 1 plus 1. Since there's no x to it, and it's just a constant, we need to reintroduce the x as part of the integration rules. And this goes from 1 to 5. Careful, work out the math. 1 plus 1 is 2 over 2 plus x. And again, we're taking this from 1 to 5. And I'm going to simplify this a little bit further out. 9 divided by 3 is 3. 6 divided by 2. And this is x. And we're integrating this from 1 to 5, meaning I need to substitute wherever I see x as 5, and do the same thing with 1 when we're subtracting. So 5, 5, 5, and 1, 1, 1. Copy and paste. Plus, and all of this is being subtracted by this. Carefully work out the math. 5 to the third is 125, times it by 3 is 375. 5 times 5 is 25, times it by 3 is 75, plus 5. Minus 3. 1 to the second is 1, times 3 is 3, plus 1. Carefully work out the math a little bit more. So this is 450, plus 5 is 455, subtracted by 7. And the resulting value will be 448 square units. So again, if you were to graph this out, which you can by making like a table chart, if you put in your x values, start putting in the values in for this function, then you'll get your y's and you can be able to map those points in the coordinate grid. But, you know, I'm just eyeballing it. It's going to be like this. You're going from 1, 2, 3, 4, 5, and up to 5. So we're going to look like this. And this will take up 448 square units. This one, you have already recognized that if you have some random number a to an x power, this is just 1.03 t, copy and paste, and a natural log of 1.03. And again, apply the bounds, 1 to 2. 1.03 to the second, natural log of 1.03, subtracted by 1.03 to the first power. We can use the techniques of the polynomials. I see the bases are the same, so we can just subtract the 2 minus 1 to give us 1. And the final result will be 1.03 over the natural log of 1.03.